Hi, how's it going? So I have been doing a lot of work on an FPGA board I bought about 2 months ago and progress. So what I've been using to follow this progress is a book found called FPGA Prototyping by Verilog. So this board uses the Xilinx Spartan 3 board um, to pretty much run through all the examples. I got the board from Digilent that's fastest through Arctic 7. So I also have a different Xilinx FPGA board. So I still use Vivado and a lot of the same tools, just a different. But this book has been really nice because it covers things pretty much from the ground up. So I was able to use what I learned from my logic class that I took and taught back about 2 years ago and kind of apply it all to Verilog. Because in that class we did some like gate level synthesizing stuff, a little bit of Verilog. This was a really good way to start from the bottom up and apply what I taught 2 years ago and doing my own project. So the book first covers gate level combinational stuff, overviews how you actually synthesize Verilog code to an FPGA, which is I use Vivado and a text editor. Other combinational stuff, it just has a bunch of stuff overviewing syntax. Some of this I was familiar with, some of it was learning for me with how to design test benches. Have some sequential circuits, go into state machine data path, and a couple specific things they cover, special cases with Verilog. And then it goes into some I/O modules, including UART, using PS2 keyboards and mice, and that's about the point where I'm at now. I just today finished the PS2 keyboard chapter, and most of these chapters provide uh, an example of how the code works, like UART process and how it sends data, how you can send and receive data, and a very bare bones module and how you can complete that. And then it kind of suggests these might be ways to test it, or this is synthesize it. And then at the end of it, they have suggested experiments where you can add more control over like UART example. One of them was a full featured UART where you would cover adding a parity bit, doing error detection, controlling the baud rate from switches, all that. So then you could modify it as you were going instead of right when you synthesized it by setting parameters. There's other ones too where it has like automatic baud rate detection. I skipped that one. I did one with parity detection. I also did one with UART controlled stopwatch, where basically I use PuTTY on my computer and send ASCII codes uh, through UART to the board, and then it reads those and then controls a stopwatch module that I designed earlier in the book. And so it's really useful because earlier in the chapters, the experiments will have you design this basic stopwatch, which just uses a counter and a clock divider, count every millisecond. Initially, you have the switches or buttons to control it on the board to like start, stop, change the way it's counting, reset it. But then you can control it through PuTTY on your computer, and then on the PS2 keyboard, you can do it with a keyboard that's not even connected to your through a different communication interface. Very similar. But that's about where I'm at. Looking ahead to stuff that I'm probably going to work on in the future. I have the PS2 mouse, which uses 3 different bytes to communicate different data being sent from your mouse, like what button you're pressing or how much you're left or right or whose complement. And or two's complement bytes, sorry, integers, a lot more bits. And then it also covers some memory stuff, external SRAM specific boards, um, stuff. And then it goes into a bunch of different VGA controller chapters, which pretty much just cover the end of it is basically designing a Pong game. I might touch into this, but I also might go into some other stuff. I would like to experiment with ADC or displaying some type of signals, or maybe doing some video, audio, image processing, something like that. Not really sure. FPGAs seem very powerful, and so I'm just kind of getting all these building blocks and working. But before I could even get to that, I kind of had to start at the very beginning of this book and learn about how to multiplex a 7-segment display, make a clock divider, write up a basic test bench, how to even synthesize and program my FPGA. It used the basics of like debugging all that on your topics basically, which this book has done a great way of building it up, and I feel like I could branch off in different directions just based on my interests. So I'm really excited looking forward to it. And I guess the point of this video was to kind of show that this is kind of my launch pad for a lot of other FPGA projects because I've been really interested in it recently, and I think it would tie really well into the other work I've done doing circuit design and board design, because if I had a very fleshed out project, maybe I could design a board specifically with an FPGA on the board, put the FPGA on there, and move it away from just like this development. So I kind of just wanted to go through some different code and just talk about what I learned from it. And then I'll also record some videos and show what me interacting with it when I actually synthesize it, because I think that hands-on experience is really satisfying to see, especially after you debug a problem. So I'll just kind of go through the code here, and then I'm probably just going to lay over videos on record at a later date. So when I started, I did not, my first project, each chapter I broke up into a project which contained a couple of different like hierarchy top level modules, and they all kind of share them. And once I designed a 7-segment multiplexer module, I've ported that over into every single project, so it's very useful to start out with. But the code here, we can see like very, very basic, like a 4-to-1 multiplexer. And I do use VS Code. I got this hooked up a couple days ago. Text editor is so much better than the built-in one in Auto. One setting you can have just to export it to another text editor if you give it the bin file.exe. So yeah, really basic. I've done a little bit of Verilog to this extent. Like I was very confident doing just with like case statements, but like I wasn't familiar with the case statements that you could use with like the case X statements or the case statements where you could include like don't cares in them. And nice for priority encoders, for example, where you don't have to write out every single case if there's like 4 bits. You could just write like 5 cases with the X's instead of 16. So here, you can just see really basic, like multiplexer, you know, this priority encoder. Yeah, so you can see the case X statements here, like bit concatenation, really basic stuff. The goal here was just to get syntax correct, get familiar with setting your input and output ports, working inside of the Vivado toolchain, and using really basic examples. And none of this is synthesized yet. I think I had a separate project for it. Even just a comparator, like I was doing like some logic stuff. We did a lot of this in my CPRE 281 class that we taught and that I learned about 2 years ago. I don't do a lot of like gate level stuff like this anymore. It's a lot more case statements when I'm doing like these part of the stuff. But it does have its merits too. It just gets kind of bloated the larger your projects get. So then what? I don't know. I got like a barrel shifter here. Just stuff like this. It's pretty bare bones. But then I did make some basic simulations to run it in a test bench, even though I didn't synthesize it. And so you can see that here. And so let's just check out the 4-to-1 multiplexer. So first, what I did is I set the inputs as the reg type, so they're registers, so that they basically store the value, and then as I update them through the test, that'll get fed into the multiplexer unit. So then like I have my inputs, which is X, and then my select line, which is S. So there's 2 bits here, and then 4 different inputs for the X lines, because it's a 4-to-1 multiplexer, so you need 2 bits for a select line, and then you can have up to 4 inputs. So then pretty much what I did was, test bench was very basic. At this point, I was just using one initial begin block, and just to state the module, and I could just run through each possible input because the code was so small. And so here, you can see, okay, the least significant bit is 1, the other ones are 0. So then I set the select line to 0, 0, so then the output would be 1, and then that's the only one that could be 1. So then I update it, so then the next bit is 1, the other 3 are 0, and then the select line picks 0, 1, so then it would pick. So then if you run this, I'm not going to run every single file, but to do this in Vivado, you just set it as the top file, and then you run the simulation here. One thing I've been thinking about doing is getting more familiar with TCL and getting these make and compile files automatically as a script I can run, just so I can automate more outside of Vivado, at least the GUI of it. And I'm hoping that could save me some time. I'm already been working out of a different text editor, which I think, and just it has like auto formatting and just better syntax highlighting. VS Code I've enjoyed in the past, so it's really nice getting a couple Verilog extensions hooked up to it. But then after you run the simulation, you'll get a waveform here, and pretty much you'll see, as a select line goes, the output is always 1. And so it never changes because as I change the select line, I'm also changing the bit that is outputted. Oh, cool, it works. And this is something I would have done in 281. So I wanted to get familiar with something I was confident in doing in a new tool, just so I wasn't also learning like new topics. Like I didn't want to jump in just with something like UART, which I am familiar with putting in C on a microcontroller, but not in Verilog. So learning that low level, not jumping in with new code and a new tool chain at the same time was really nice. And so that's pretty much what all these projects were for. As a note, I will add a link to this in my video, but I do have all of these in a public GitHub repository. Each of these projects are in a separate folder inside of the Git repo. So if you want to look more into these, feel free, but I'm not going to go through all these like super basic ones just for the sake of time. But then in the next project I had, so you can see these are all the projects I have. The PS2 Mass one is empty. Started that one. We were in starter code, so the next one was synthesized starter code. So then I'm going to open the top level project folder, add before. And so yeah, my goal is hopefully going forward, I can move away from using the Vivado GUI as much as I can and just get those separate files, because I've noticed a lot of my dev time kind of gotten slowed down based on just going through Vivado, and working on, working out of VS Code has been really nice. It's kind of hard because like seeing the hierarchy view right here is nice. I need to find a convention for that. But so you can see I synthesized a few things. I also, I don't know if did I test any? But so the big ones that I would see are, like very basic. The first thing I started with was blinking an LED. And so I always have the synthesized module as a top level one that instantiates the blink one. I don't include so these are the input and output ports that are in a constraint file for the Bassist RTX 7 board that I use. And so it has 16 switches, 16 LEDs, looking at it right now, 5 buttons, 4 7-segment displays, and then a USB port, a VGA connector, and some 16-pin connectors for PMODs. One of them is connected to ADC, stuff like that. So whenever you want to use specific parts of it, you uncomment that out in the prints file, which I just found one online. There's a copy, so you can see, you got 100 megahertz clock. You've got 16 switches, 16 LEDs. These switches and LEDs and buttons were great for like starting out, and then now I've been branching out using the USB port for the PS2 stuff, or the other USB, the micro USB port that I've used to program the FPGA can also be used as a COM port for UART and PuTTY on. So it's been really fun being able to branch out of this and just slowly build pieces up. And I think with digital design stuff like this, that's kind of the key. So looking at this blink LED, let's see here. Man, this code is like, I haven't seen this in a while. This is kind of interesting. So I guess I had 4. Oh yeah, okay. So I was like, why is there so much code in this? I thought it was just one LED. So it is one LED, but it looks like I had 2 switches, which this is kind of funny. Like I could have made this like 2 bits and like 1 port name, but shows when I was starting out. But pretty much what I did is I could select between 2 switches to turn the LED blinking at different times. I think when I started this, I had the lesson of making the frequency too fast to where as it blinked, I couldn't visually see the light dimming because it was just flashing so fast, or it got to a point where it's flashing so fast that like it was kind of dim. So that was interesting. That made me ask a couple more questions about like what I was actually doing and what I was seeing, and that was a really good lead into the 7 segment displays, which I think for this I just had one display. Let's see. No. I did have the 7 segment mux. So I've used this module for everything. At some point, I added a PWM module where I basically control the percent of time that it was on versus off. So basically, what you could do is you could dim the 7 segment display so that basically it had a resolution of there were 16 or sorry there were 4 bits, so you could have a resolution up to like 15 and 15, 16, and so if you input 8, then it would be at 50%, and you could control how dim it was. But I didn't have that at this. So the Sega port is the 7 bits that control the segments of each 7 segment display. And is the enable pin for each of the 4 displays. And something that was really interesting that I didn't think about is you'd think that like you would need 7 times 4, 28 pins for these 7 segment displays. But what you actually do is multiplex between this enable so that through this module, it just alternates with a counter in the 4 most significant bits to pretty much just flip between each display so fast that you can't see that it's turning on and off. And so that was a really cool key to think about from when I was Blink LED. And so what you can do is I just have a module where I just feed it data. Oh yeah, I think at this time I had it so the display was all 16 bits wrapped together. I think later what I did is I separated them into the 4 different displays just so it was easier visually to understand what was going on when I was inserting hexadecimal values. And yeah, pretty basic. This was one that like was really fun to just test and learn and do because I got to figure out how these 7 segment display output ports worked. Got to play the switches more, and stuff like that. But pretty basic still. And we move on to what we got next. So I think then we started in chapter 3, which is combinational logic. What's that? And at some point, I'll show another test bench that's more interesting. Yeah. So we got something like a barrel shifter, dual priority encoder. The synth ones just display. They normally just put at this point the combinational stuff. It just used the 7 segment mux and then whatever other module I was using at the time, like this encoder module. And so it looks like I had 2 separate modules for the first and second encoder. Interesting. I haven't looked at this. But yep, so same way, I just used the case statements and it was 12 bits long. I'm pretty sure I just threw that over the second one. Yes. Yep. And yeah, so stuff like this. The BCD incrementer was pretty cool. So BCD pretty much let's see here. Let's go into the actual code. So yeah, at this point, I instantiated 3 separate BCD modules. I also, could have included it all in this module. I think at this point, I was really interested in seeing that hierarchy play out and just save code. But it's pretty basic at this point. If the input is less than 9, then you will increment it. And make sure, I had an enable input in here. If the enable was not on, then you would keep the same parts and then yeah, output would stay the same as the input. If the enable pin's on, they'll increment. And here, if bug benign, output 0. Oh yeah, okay, so it's an if statement. So pretty much if the input's less than 9, it'll just increment. But if it's at 9, so normally with a 4-bit input, you could go up to 15 or hexadecimal F, right? But so with the BCD incrementer, then you pretty much want to go 0 to 9 like you would in decimal. so that if you're at 9 and you need to increment to 10, well, you can't show 10 in one 7-segment unit, so you go back down to 0. And then that's when you would have a tick and then include in the next one. So that's kind of the code that I use for the stopwatch stuff. And, we just kind of keep incrementing it here. But I can show another test here. Let's try this one. Take a look at the code. So very basic again here. I had a delay here, which I think I ended up, I guess I didn't really use a clock in these yet because it was just combinational stuff. Yeah, that's interesting. But yeah, so these initial begin blocks will all happen at the same time. So like on startup, I set things to 0. Pretty much BCD in. But pretty much you also can have a separate module. I have a separate initial block um, for alternating the clock. I guess I do have, yeah, I have a clock because I also included these 7-segment mucks, and then I have stuff for BCD in and so on. And so we can run this in. Might get mad at me because I was running it in another project. I guess I closed it. Should be good. So here we go. So you can see here the switch initially is 0 at the beginning, and that is because of this initial block here. I'm going to have to set delay, which this delay I renamed to T in my later test benches, which better represented the time period of the clock, which affects a lot of stuff in time. But so you can see here we have one 12-bit input. Really curious. Oh, I know why I wrote this. Okay, yeah, so I think I did this just so I could increment the input to the output, because pretty much what it does is it just increments the BCD input by 1, and then I would set that input for the next point to whatever the output was, just so you kind of get this feel of a counter during your test bench. And so, your input is 1, your output's going to be 2. But if you go up to 9, then the next bit in pretty much, so the second bit, well, I guess, no, sorry, there's 12 bits. So, you'd break it up into X bits. And right now it's representing this, and it's pretty cool. I enjoyed doing this. It's pretty fun. But yeah, and then you can see here I also have the 7-segment displays down here, which you can go and you can. Oh, those are the seg points. Yeah. So okay, and you can see as we go farther and farther that the test benches will start getting more elaborate. So if we go to the part here. So then at this point, I started doing, what was, looks like we're just doing a lot more combinational stuff. This might have been the point where I started doing state machines. I think it is. Yeah. So I started doing things. I started designing modules like a clock divider that was separated. I made a stack. I also made a first in, first out module that I used as a buffer for my UART stuff and for the PS2 transceiver stuff. And then, this stuff is easier to see, but we can just kind of pop into one. So this circuit here, this heartbeat synth, what this does is it represents something similar to a heartbeat at 72 hertz on a 7-segment display. And so I'll show a video of this. It'll be a lot more telling than talking about it. But pretty much it just has 2 lines that go in and out based on from the center of the middle 2 7-segment displays. And so, I made a separate 7-segment multiplexer for this just to make the code easier. And I also have this heartbeat, which basically tells you, I have this dot line wire, which is 4 bits, which basically tells you which line on each display should be on. And so then this multiplexer interprets that instead of using the hexadecimal values for the multiplexer to read it. And then we can hop in that to state machine. So the code's starting to get a little more complex, right? The input for all of these always have a clock and a reset. All of these are synchronous with an asynchronous reset. So you can see here at this always block, at the positive edge of a reset, it will set the counter to 0 and like, yeah. So I had a counter for the clock frequency and then another counter for the state of the rotating squares, which I also called count, which is a little confusing. I'd probably rename that going back. But you know what? That's how we work on it. So I also had an enable pin, so the heartbeat would not move unless this enable pin was set to 1. Then the outputs are the enable pins for each of the 4 individual 7-segment displays, and then the line to say which the line should be on. And so pretty much then you can go down here. So this DVSR counter was basically a modem counter for a 72 hertz heartbeat. So if you remember what I said before, is the clock for this board is a 100 megahertz clock. So you can use that to think, okay, well, if I want a 72 hertz signal and set it so that that 100 megahertz clock counts up to this number to get a 72 hertz frequency. And you can use this also for certain milliseconds. I use it for the stopwatch. It really just depends how fast you want it to. And this is really tricky because I found that like when you're making a test bench, the time unit is default at nanosecond, and normally you don't want to run a when you're synthesizing it, you want that time to count up to be 72 hertz. But if you're doing it on a test bench, you want pretty much all of your things counting to just be faster, and you want to see the logic in it. And then when you throw it on the FPGA, you want to make sure the actual timing of the counters are correct and just like extend it. Because if you run it's very, very rare, like the test benches I've run go up to about 20 microseconds. And so if you're waiting for a second to occur, 2 seconds, you are going to be running thousands and thousands and thousands of time units if it's in the nanosecond range. And that's just one quirk to it. It's another thing I've learned. So then I guess I didn't actually have a state in this yet. I guess I did. I just called it count reg. But pretty much what it does is alternates between having which lines are on, which enables are on, and so on. And then this line is basically just looks like one hot encoded, and then oh no, sorry. So 2 of the bits aren't on, so it doesn't matter output is, it looks like. And so yeah, it's a lot more telling when you. But yeah, very similar stuff. I had a rotating banner that pretty much took 10 hexadecimal values and then rotated them in order. Since there's only 4 hex numbers can be displayed on the unit, it would shift between them, and I just used a 4-bit shifter circuit for that. The stopwatch is something that I've kind of repeated a lot. Well, you'll see these top-level synth modules are all very similar. They have very similar input-output ports with the clock, a reset button, the switches, LEDs, and then the 7-segment stuff. So if you want to get to the fun stuff, you got to go a layer deeper into whatever module is actually. But this circuit I've actually still used a lot when implementing this stopwatch counter with UART module and the PS2 keyboard stuff. So it comes with a clock, a start-stop signal, which I just called go, a clear signal, which is similar to a reset signal for the counter, and then 3 hexadecimal values, which are technically BCD values that won't go above. Actually, yeah, it won't go above 9 on each of these. I changed it on all 4 of them later. But so pretty much what happens is the DVSR is set to, it would be 10 megahertz because 1, 4, 5, 6, yeah, 10 megahertz, because then you would get a tick every millisecond, so 100 megahertz counter, or 100 megahertz frequency on the clock, sorry. And so then you just have a bunch of counters for that. And so MS next. So this is where we kind of start doing the state machine stuff. And so this is a very explicit version of it where these registers are getting assigned to the next values, which is just combinational logic. And then, these are blocking statements, and then these non-blocking statements up here are assigned concurrently. But these are executed one time. And one thing I did learn through the book is it's always important combinational logic blocking statements, and for sequential logic like this, you want to use non-blocking. So that's kind of why I split them up like this. And then these will get assigned every positive clock edge. But since this is combinational, this will just always be running all the time. So yeah. And then pretty much, the go has to pretty much to increment or get set back down to 0 if it's at, so I guess this MS tick pretty much every 10 million counts, or every millisecond when you're on the actual FPGA, it will assert this tick value, which means that this D0 counter can assert an increment, which this D0 is the same as pretty much this MS tick, where it'll just, D0 enable is the same as it, so that every millisecond it will increment. If it's at 9, it'll get sent back to 0. Otherwise, it will increment because, like I said, with a BCD counter, if you're at 9, you go back down to 0 because you can't display 10 on one 7-segment display. It's just 0. And then what happens is the D0 tick is enabled whenever the D0 reg is 9, and at the same time, you'll notice it'll go back down to 0. So if you think about it, you have, okay, so if you have something like this, right, and then you increment again, right, you're going to go 1, 0. So as this gets sent to from 9 to 0, you need to represent that with the next decimal in the 10 spot to represent a second has occurred every 10 milliseconds. So that's the idea of a BCD counter. That just kind of carries through for all three of these, and it's a really cool thing. It's interesting to think about when you're working in binary and these hexadecimal values go up to 15 and they represent F. Because if you have a counter that displays F milliseconds, that's actually 15 milliseconds, that's not practical to read on the fly. And, so that's what this is used for. And I've used this module a bunch, a lot of similar stuff like this. I'll probably show a couple other ones. Hopefully I'll have the rotating band. But then we have chapter 5. Chapter 5, I think, state machine stuff. So let's see. So yeah, we had a couple different things that were specific to book. So I had a dual edge detector, which basically detects a rising and falling edge of a button or a switch or so on. And then I also had a debouncing circuit, which, let's see here, I had a lot of code in this. I think this is just to synthesize it to make sure that it worked. Yeah, so what I did is I had a counter that had a rising edge detector for a button that was debounced and one that wasn't debounced. And you could see as I pressed it really, really fast that the one that was not debounced would increment more, and it would kind of show, that it wasn't debounced. So it, based on glitches in the system, it might actually count when you don't want it to. And when you're just doing something like a counter, that might not be a deal. But think about all the digital applications in the world that could be an issue for. So pretty fun to learn how to just do a basic debounce circuit. And we can go into it, I guess. So inside of that, I have the clock divider, but I think the idea was that it would have to, yeah, so I did start using states here too, so that it would start 0, and then this was assuming that, like, as you were pressing the button down, the default case was on my board. So pretty much the next state would be determined that if the switch or the button was being pressed down. So if it was starting to be pressed down as a 1, then you would go to the old 1 state. Otherwise, you would stay in the same state, which is Once there, then you can set the debounced output to 1. And then pretty much what you would do is you would stay in this state. And so there are a couple different ways that you can bounce it. Um, this way, I think that what would happen is if you think about a debounce button bouncing as it gets pressed and released, immediately as it pressed 1, it would hold for a set amount of time, and then it would stabilize at 1, and then immediately as it pressed 0, you would go back to the next state like this. And so you could do it the other way, where once it detects a 1, you hold in 0, and then you check basically after this MS tick, which so it would wait 20 milliseconds after you press the button down, and then after that point, if um, MS tick was 1, then you would stay in this state that you are, or you would you would move to this state where it is confirmed to be in 1, and so you set dB to 1. Otherwise, you stay in this hold 1 state, and then as it is 0, go through here. Then you check the switch again. So then at this point, it can either stay in 1, or if you drop to 0, it'll drop right away. So then I can show an example of those two counters, how those work. I'm trying to think actually which one this is, because I think I just got that mixed up. So when you press 1, you would go to hold 1 immediately. And then after this tick, which is 20 milliseconds, it'll check again. And then if it is 1, then you go to the actual 1. Otherwise, oh yeah, okay, so yeah, what it does is it waits 20 milliseconds in this state, outputting 1, and then after that 20 milliseconds happens, you go to 1, and then here it'll check basically to where, okay, if the switch is still 1, we'll keep outputting 1. Otherwise, we are going to set it to 0 and wait 20 milliseconds. Yeah, I also had one where it was like a parking lot counter where I used 2 different inputs that were like spread apart, and basically as a car came in, it would increment the counter, and then as a car came out, it would de-increment the counter. And so this was just another like fun thing to think about with a state machine, and just all these different cases where you got to think about the 2 different branches where, okay, what are the inputs of the A and B inputs if a car is coming in, because it initially will hit one sensor coming in, then both, B sensor, and then none. But then if a car is leaving, it'll first hit the B1, then both, then A, then none. So you had to have both those branches and think about what would happen if you leave them. So pretty classic like state machine problem. But those were the big ones. I also had those dual edge detectors. Pretty useful code to. So that was chapter 5. I'll go to chapter 6. I think chapter 6 was finite state machines with data paths. So you would, based on the state you were in, and then take certain functions and then that to your advantage. So what did we have here? What's some fun ones? Yeah, let's just do this Fibonacci. This one's pretty basic. So, we just used a state with, it's really messy here. So the book helped explain. Oh, yeah, okay. So I converted it to output it on the 7-segment display. So yeah, we have some different states here. Basically with the different Fibonacci circuits I was working on, where we had an idle state where you would set the inputs with the switches and then hit begin, and then it would compute. Basically, you would provide it a number, let's say 10, so then it would find the Fibonacci number of 10, where it would add 0 and 1, 1 and 2, 3 and 2, 5 and 3, so on. And so then what happens is you had this conversion where idle, and then once the state began, you basically begun under this start condition. So you press a button and say start, and then you basically set the state binary. So you convert the input number, which was two BCD numbers, which basically would just control, um, you know, the Fibonacci number that you were going up to. And so then you could display those text display if you wanted to. That's why I used the book suggested it, was that convention. And so pretty much what you had to do is you would set those BCD next values. Very literal description of the state machine here, where the actual registers are all assigned non-blocking assignments here. On a reset, most things are 0. The state reg is sent to the default state, which is idle, which is ready to begin. Otherwise, the state or whatever registers are assigned to their next values, non-blocking ways. And then in this always block with SMD stuff, you pretty much, the next values are blocking statements assigned to what their registers were, so by default they won't change. This makes it so you don't have to assign these the same in every single case statement. That's why they're included before. And then you just have a basic case statement for the registers, and then I just use parameters to assign these with 3 different bits so that it's easier to read, because if in here you had state reg equals 0, you're like, okay, well, what does that state mean? So I just called it idle, because then it's very clear that, okay, it won't begin. Input start, not asserted. Default should be held at 0 whenever a button. So yeah, and pretty much for the BCD to binary, you just convert the 2 BCD values to binary, and there's a function that I learned about and looked up where you can do that, and so on. And then you have the actual Fibonacci sequence. I think this code that I had in a separate module to test to begin with, find it in the block. And for the actual Fibonacci sequence, pretty much what would happen is, if you were done with the conversion, then you would basically set the next value and then the next state as Fibonacci, and then pretty much you would just have it. So n is basically the number that you would use for how many Fibonacci sequences you're incrementing, and that's what you converted in this BCD to binary phase here. You can see Sn next equals Sbin next, which is what you convert through here. And so you kind of use Sn for a couple different things here. Like here, it's used to decrement down to 0 to know how many bits to convert and shift from these BCD values. But then here, it's used to represent how many times it's set back up to that number, and then it decrements again. So if the input is 0, then pretty much you use T1 and T0 as your 2 Fibonacci numbers, and then you just output T1 because that's your at the end. So if it's 0, then T1 is set to 0, and you're pretty much done. You convert it back from binary. If it's greater than or equal to 21, then you just set T1 the maximum number that it can be, because 21 is greater than decimal 9,999. I forget what it is. It's like 12 or 13,000, something like that. And then you go and you convert it. Otherwise, if it's 1, then you convert it. And so what happens is, if it's none of these cases, then what you do is for T1 next, you add what you had it for T1 reg and T0 reg, like, and then for 0 next, you assign what you had for T1 reg. And so it's very simple, very similar to just a recursive problem, very similar to something I've done in other classes in Java or C before, but just applied in Verilog. And this makes you think a lot more about like the bit conversions and thinking like really low level about it, but also still applying those ideas. And then if state next equals bin to BCD, which if it is either 0, greater than or equal to 21, or it decrements down to 1, then you set the BCD next values to 0. Pretty much just convert back to the BCD values from the binary output, and then this can be displayed on a 7-set. Yeah. Then there's also this one. This reaction timer is really fun. So this one, 7-segment display, and then you have the actual. So this React module is, it just uses a pretty much just like that stopwatch counter, and it just kind of increments here like this. And so that's just for the display, basically. That's also FSMD. And so then, you have the tick displays and the enables, which use the other ticks. So this basically is just the counter. And so the goal of it is that after you hit start, then you okay, yeah. So I forgot about this too. So high is displayed at the very beginning, and so I have this special multiplexer here where A and B basically just represent um, H and I, which is not part of the like hexadecimal display I had before. So I had a special multiplexer unit for this one. Basically, if it was any of the hex values, it would display these letters on the middle too. And then you can control the B and the AN from the 7-seg displays. Once you begin, you turn off high from the display and you set the state to random count. And then otherwise, sran next would equal sran count. So I don't know. This coming from. I don't know why I assigned that there. Interesting. Maybe we'll figure it out as we go through. It's been a bit since I. So when you're in the random count phase, pretty much what happens is the 7-segment display turns off, and high is not displayed anymore. But once it shows up again and it starts counting from 0, you have to hit a button as fast as you can, and it stops, and then you get to see what your reaction time. So then in this random count phase, it randomly counts between 2 to 15 seconds, and then the segment display is off, and so on. So what happens here is if you hit the stop button while in this random counting phase before the 7-segment display turns on, all outputs get displayed to 9, and it's basically like you reacted too fast, or you preemptively hit it, so you have to retry again. And that's the highest case statement if you hit it too early. Next, if the random reg decrements down to 0, then you go to the react phase, where all the counters are set back to 0, and it'll start incrementing. Basic millisecond timer counter, like the stopwatch. It's very similar code, just applied to different. Otherwise, increment the count. And so I guess here, sran next equals sran increment. So then, I'd see here. Okay, so temporary count wires to increment registers. So the segment ones are just the count. Oh, yeah, okay. I remember how I did this. I was really stuck on this because I was like, how do you get a random number? That's why I have the SRAM next here. I was like, how in the world do you get a random number in hardware like this? And so what I did is I had a hidden counter running while it was in the high phase. And based on when you pressed it, it would increment really fast between 2 to 15 seconds. And, it would default back to 2 when it would increment. But as it would go through, right when you pressed it to begin the game, that's what it would lock in the time as. And pretty much that's why this is here, because if you don't begin the game, then sran next equals sran count, which this makes so much sense. Okay, I forgot I did this. I was really interested in this when I did it. Yeah, because it's a 4 bits, so it increments between 2 to 15. So if you go to sran count down here, you can see that if it's 15, then it'll go to basically 2. Otherwise, it'll increment. So it's a 2 to 15 second random counter that just ticks really fast. And based on when you press it, you're going to have no way for a 100 megahertz clock to time it to predict it. So I forgot that was hidden like running in the back of this high display. But that was really cool. I was really interested in it. But yeah, so then you have that set random count between 2 to 15. So then you have sran decrement over here, which pretty much it just checks when to decrement that random count that's between 2 to 15. And so the maximum segment display, because it's milliseconds, and then like 2-second counters that go up to like the 5 and 9, maybe 9 and 9. Let's see. Hmm. Yeah, it looks like it does go to 9. Maybe it's just second. No, because it's got that DVSR there too. But pretty much every time this MSB 7-segment display happens, second will occur, and then this would decrement. So this SRAM next doesn't always need decrement, so maybe I could rename that. But you can see here, if SRAM reg is greater than 0 and seg3n, which is basically just like the tick to enable this to count one more time, then this will decrement. And so I used the same counting variables here. So you'd think, okay, during this random time, right? Nothing is displaying, right? Like nothing, the 7-segment displays are off, right? Because you don't want to guess it. You want to hit that counter in the next state, not in the random count state. So I just use those counters that are wired up to the 7-segment displays, and they're just off, not actually displayed. And that is done through this here where it says S and next equals 4-bit. So that's pretty cool. I guess if I was doing this, like it would probably be better to put this like here if I was going back, because then so this is the next value, right? So as that state gets asserted in the next clock cycle, it'll begin random count and it'll get 52. But it happens so fast that you just aren't able to see it. But going back with what I've learned and testing some stuff, that's what I probably would. And then on the react phase, it's just a basic counter similar to the stopwatch thing. It's pretty much the same code. If the stop count reaches 1 second in this state, then you will be done. You lose. Want to react faster than a second. Or if you hit the stop button, you are also done, which is. But yeah, I don't know. I think I added the stimulus bit here with the done tick to like something fun. Like I wanted it like the 7-segment display to like blink or something with another state. Looks like I never got around. This was a really cool piece of code project. So let's see what we have for code for it. Action. So we'll set this and run it. So we can just kind of see what it actually was before we run it. So now you can see here I have a different always block that increments the clock. So every half of the period, which is defined as t, the clock will change from 1 to 0, so on. Initially, too, I always apply the reset button so that the state machine can get its default values assigned after a reset button is pushed. So this also happens within the first, because it's an initial block cycle, because it's also driven by the over 2. And then, resets set down to 0 in the bench. So at this point, I also wasn't really using tasks. Whenever I started doing UART stuff, I designed a couple tasks to basically collect the receiving or send out the transmitting portion so that it'd be easier to read ASCII values and so on. And so, for this test bench, you pretty much begin by assigning the regs or the inputs start and stop to 0. The other ones clock and reset already. This is just so that you have your ideal condition. And then you wait for the initial reset to deassert, and same with the clock. And then I also waited a bit more. So then pretty much what happens is you're in that idle state, right? So then if you hit start, and then you wait a bit and you deassert start, because it's just a button press, right? So you let go before the next state happens. You gotta keep track of your inputs. So positive edge stimulus. So this is pretty much the done tick. So this is when you're done with the whole unit. So you want to wait until that point. Or no, sorry. What stimulus that? It seems like that's when it. Yeah, okay, so sorry. Stimulus is asserted when React is active. So that'll be active that entire time. So what I did is I waited until the positive edge of that so that after the random count, it starts to begin counting up. So then you wait 20 turns and you press the stop button, deassert it, and then wait. So pretty much this is just like the ideal conditions of the reaction. wait a random amount of time, you wait for it to begin, and then you press the button before it runs. This condition here is what happens if you press stop button before the stimulus is set, so that's why I don't have this pause edge stimulus wait here. And then after that, I have one where you don't hit the stop button, and so it's active for. So this was a pretty interesting one to think about different cases for a test bench. It's not super complicated, but it does get you thinking about different edge cases that you can have, and I'll show the waveforms for that. Same thing, run simulation. So a lot of this stuff is very rinse and repeat, which makes me want to some issue here. I'm gonna close out of this because I think it might not like that I have code open. Oh, there. No? Not find port ORAND on this reaction timer up. Oh, you know what I did? I think I tested it and I had this extra input in here. So let's check the reaction. It looks like it's looking for a port that doesn't exist. Yeah, so we can remove that. Normally when I'm testing, I sometimes add in other ports like representing like what state you're in, just so it's easy. Understand, you know, where your code actually is, because if you're not outputting correctly, you kind of have to start thinking, okay, what state am I in? What data is not getting outputted to IO in this model? And there's a lot. So doesn't. Line 40. Delete this now. It didn't save. I don't think it saved. The computer's really slowing down right now. I don't know what. It's been running. Oh, this is unfortunate. Well, might have to wait on that. I don't know why that's slowing down. But that's okay. We get the gist. So we can, which was UART stuff. So UART stuff was really beneficial. You can do a lot of stuff. PuTTY, serial ports. So I had a couple of different ones that I used UART in. Basic one that I kind of learned from the book was just a basic UART module, and then I implemented a little more to it. Also had it where I controlled these stopwatch functions earlier with UART module done through PuTTY and my keyboard on my desktop PC. So to begin with UART, this was definitely the most complicated thing that I did at the time. Yes, code is like. We're just gonna try again. So, you know, this UART module, what I did is I had a receive and a transmit module, and then both of those had a first in, first out buffer. And I also had a baud rate generator, which was basically just a clock divider to determine the baud rate for the UART module. And in this basic one, it just assumed that you would use 8 data bits and then 1 stop bit. And it had the counter for a baud rate set to 19,000. In the full one, I had it so you could customize these things with switches before beginning transmitting things. And yeah, that's pretty much it. I can go into the receive and the transmit are very similar. It's just whether you're sending bits out one at a time or in one at a time with start bit. So we can just go into the receive function and kind of about this for a minute. So let's go here. So pretty much what happens is on a reset, you go to this idle state and then you set your counters. Um, Pretty much with UART, it's idle data bit. So with UART, there is no clock. You just agree on a baud rate before sending just like one data line that alternates baud rate. And so pretty much what happens is when the start bit occurs, which is when it goes from a idle, which is 1 to 0, then you can begin. So the state next would begin start, and then pretty much what happens is every bit I oversampled, so I sampled 16 times per this like IS tick, which would come from the baud rate generator, and so it would sample 16 times per bit. And so that pretty much it would sample the middle bit, so that hopefully it would sample the correct value of either for the start bit, for the data bits, parity bit, stop bit. So that's why it waits till the middle of this start bit after detecting it. So like you can think about it, if it samples 16 times and you detect it gets pulled down to 1, you want to wait 7 more times so that it's like 8 in the middle before you actually measure that. And so what happens then is you can go to the data state and then you can set your counters. And then so for every tick, basically, if it isn't at 15, then you increment it. If it's at 15, then what you do is you measure that bit, like I said, because you sample 16 times based on the ticks from this baud rate generator. When you do get to that 16 samples, it pretty much what happens is you shift in the bits because it'll send them one at a time, and you receive the least significant bit first. And so you have this RX bit, which is the receive bit they sent from PuTTY or from your computer, and then you pretty much shift the other bits in the register, which if you notice here, SB reg, it is set to 0 initially, and then it's just shifted out. So that as you receive more bits, so you'd first get this LSB, it would come in as mostly, and then every single bit as it reads over for bits, it'll get shifted right more bit. And then you put a stop bit, which you also wait for that tick, and then pretty much what happens is you wait for the X amount of ticks for the stop bit, because the stop bit can either be 1, 1.5, or so in this case it would be sampling for 16, 24, or 30 ticks of this baud rate, which is what you can see SB tick parameter, which is defaulted to 16 UART because we wanted a bare bones module, so we just said, okay, it's going to be one stop bit, just so we can do it. Then the other unit, the UART full module, just, I had different units, UART RX full, UART TX full, first in, first out full, baud rate generate full, which basically, instead of having all of those values set as parameters, I had them come in as inputs from switches that I could board, and then I could manually change them on PuTTY on the computer side of the end. And I pretty much just use the basic UART one for future stuff just so I can agree on it and do it faster, but this is a fun way to apply it. It also does include different errors, like, talk about it here. So 3 different errors I included. One was the parity bit error, because I added a thing where it'll pretty much invert a bit based on the parity that's reading if it's odd, and then if it differs from the parity bit end after counting its own data bits, it'll be an error. It also has a frame error, which basically could boil down to your baud rate being different, and it just checks whenever, pretty much at the end, if your stop bit is 1 and then the bit is 0, then it'll raise a frame error because they're mismatched on the data. Bit 2 is data overrun error, which basically means overwriting data in your first in, first out buffer, and so you are not processing information as fast as it's coming in, or Yeah, I think the data run overrun error is just in the receiving unit. Uh, Actually, yes, because what happens is you have this error assigned kind of at this top level module you are full, and so if the receive is done and at the same time the receiving buffer is also full, then it's going to overwrite whatever the first input that came in was. First in, first out buffer. So those errors were really um, fun to test in a test bench. It's harder to raise them on the actual UART module. What you can do is you can set the baud rate different. You can set the FIFO word address buffers to contain less amount of words or like data going in of them. So like I have 2 address bits here, so pretty much it'll take 4 different inputs of data or 4 bits, but you can make that smaller and try and make it like overrun itself and so on. Parity error also, you can set like 1 to even parity, 1 to odd parity. Bit difference when I flag that error. The number of 1 data bit wrong. But yeah, I might include a separate video of just like all the demos just for people to see. But yeah, the stopwatch one, very similar to where I just control on the keyboard commands on my computer. It sends it with pressing like G for go, P for pause, C for Q for up, down, which basically reverses the direction of the counting. So it's just fully implementing enhanced stopwatch that I did before. And then if you hit the R button, it'll actually transmit back the data, the BCD values in ASCII text of pretty much whatever the current time is. Stopwatch. So it's cool because you actually can do that, and you don't actually need these 7-segment displays on the board. One thing you could do is play it like every second with that receiver. Then finally, we'll go. So the way that the PS2 system works on a keyboard is that there is a PS2 data pin and a PS2 clock pin. So unlike UART, there's a set clock that's divided by whatever the device is. It basically sets so that every time you have either a positive edge or a negative edge keyboard. So let's go to this basic PS2 receiving system because we don't need to transmit anything keyboard. So we just have this PS2 data coming. PS2 clock. So what happens is, the book I kind of learned about this clock filter where pretty much you would only, so you kind of want to debounce the clock because based on if the clock is at a falling edge, then you will basically read whatever the data pin is at that point. Start bit, your 8 data bit, your parity bit, stop bit. That part is the same as you are. It's just designating with this clock pin a falling edge. So this is a little like state stuff to basically filter it. And then down here, you have a state machine, very, very similar to UART, where you just hand over receive. So, your idle. Basically, what happens if you're on a falling edge of the clock, and then the RX enable is just a pin basically to enable or disable receiving from the PS2 unit. I included it here, and then I just set it to 1 for everything else, so it will always be actively put. So if it's 1, and then also if the data pin is pulled down to, like I said, the idle state is always outputting 1. So if on a falling edge and it drops down to 0 or a start, you will begin. And then, look at that. It's the same thing. You just pretty much shift in the input, and then as the most significant bit, and then you shift out least significant bit of this SB reg and keep going. Do that with this counter here so that you set SN next to 9 bits. So it'll basically read in the 8 data bits and 1 parity bit in the receiving state here. You also could split these up into a data and parity bit like I did before. I kept them as the same here. So then once it hits 0, you've read all 9 bits. You go to the load state. There is 1 extra clock cycle needed to load SB next, since these are assigned and then they're actually put into the registers on every positive edge block. So you have to wait for it to get that parity bit in. And then pretty much you just initiate a done tick. After that done tick is asserted, similar to before, that's basically telling you that, oh, you just received 8 bits of data. So now you can use that done tick to write it to the first in, first out buffer. And then with that first in, first out buffer, there is a point that you can basically say, oh, another signal bit asserted saying the FIFO buffer is not empty. And then you can send it somewhere else or use it in another circuit. So that's kind of the bread and butter. Is you receive it from here, you assert that it is done, you write it to a buffer, and then you see that the buffer is not empty, so you can start pulling in data from it. Just so I don't have to hit a button to. But that's kind of the core of it. Just today, I was finishing up the code for. I was just finishing up code for the stopwatch. I guess it'll let me. I don't think it's gonna like that I have 2 projects. Oh no, it worked. Okay, cool. So 1,000 on the time for a lot more. So you can see here, let's actually look at the testing code for this. I actually really. So, here, this is very similar to what I did for UART, where I had this receiving task. So pretty much I could just call this in my test bench. And so the way that the keyboard works is that after a break code, which is F0x, so the way you press the keyboard, if you press a key down, it'll keep repeating that key you pressed, and then when you let go, it'll have a break code and then whatever you pressed. So if you want to just have a keyboard where you key presses once, you can just read whatever key is read after these break codes. So that's how I simulate it. So you can kind of simulate a key getting pressed by receiving, oh, it's done, and then what is done, and then what key. So then it's the same thing where you have like G for go, P for pause, U for reverse, C for. So what I did is in the actual code, I converted it to ASCII, so then it pretty much was just using the same code structure as the UART one. Key codes are different. There's a lot more I could talk about all this, but I'm hoping with the demos I show and kind of what I've gone through and how much I've done here. But pick up the. We're gonna run it for a long time. So this is when the waveforms. So you can see here, this key code is pretty much unknown. So you can see that KB, the keyboard buffer empty, inserted almost always empty. But then whenever you look into ASCII, so whenever it reads a G, it'll basically put that in the buffer and say, hey, it's not empty. And at that point, then that is a signal for the stopwatch interface. Read whatever this ASCII code is. Then you can see on the next clock cycle that it goes from 0. Right after that, if you zoom out, you can see that these 4 different PCD counters are incremented. This is the millisecond counter that's set to increment every clock cycle, since we don't want to actually simulate up to every millisecond. Then you can see, it starts to increment time here. We have a P that represents pause. So then at the next clock cycle, after that right here, go goes back down to. Then over here you have U, and so you can see that it inverts up from being 1 to 0, so it'll start counting down. But you have to think go is also 0 from that. Not actually. And then I just hit go again, and I wanted to wait a little bit, make sure that it's down. You can see that it counted all the way up to 2 seconds, even incrementing faster than 2 seconds. And it starts go back, going down to 1, basically. And I'm curious why it starts at 5. Oh no, sorry, that's correct because this is the enhanced stopwatch. So the format that I have it is that most significant display is goes from 0 to next to count from 0 to 59 seconds. Significant bit. Then at the very end, I tested the clear input. After that is asserted positive edge of the clock, then it stops counting. Clear is active, so it sets back down. So all of these inputs are 0. See right here. Yes, actually, these are assigned on the next positive edge clock cycle. So it updates the go, clear, and up values. That's kind of the bread and butter of it. That's all I've done for now. As I do more complicated projects, I probably will split them up into more. This video went really, I don't want to cover some stuff I've done so far. Maybe in the future, like I'll just do a video on like PS2 mouse stuff, learning some memory stuff. But yeah, this is kind of what I've been up to. Hope you've enjoyed the demo videos. I probably will lay different demo phone just so you can maybe see like a 2 or 3 thing. Um, but yeah, so thank you so much for watching. Enjoyed it, and all this code is on GitHub and public. So if you want to look into things more or tear my code apart, feel free to. I'd love the feedback.